because Chapter 2 has a lot of introduction to energy problems that will be repeated a whole bunch. So might as well get started getting used to some of these units. So table 5.1 gives you lots of common units of energy conversion to joules, because joules is the standard unit in science, right? And last year in chemistry, you guys probably used this calorie also. But in APES, we tend to use these crazy sounding units called the British thermal units, BTUs. Still a unit of energy. 1 BTU is 1055 joules. And we're especially going to use this weirdo one called kilowatt hours, which is still a unit of energy. Specifically, we see this a lot in our energy bills. So amount of energy expended by using 1 kilowatt of electricity for an hour. So notice that when you're using this unit, it's a kilowatt, so 1,000 watts, literally multiplied by the hour. And you can see right here that 1 kilowatt hour is 3,600,000 joules, or 3.6 megajoules. We're going to use this in a little bit too. So check out this do the math that's already introducing you to calculating these kilowatt hour energy units and making sure you can convert them. So it says your electricity bill shows that you use 600 kilowatt hours of electricity each month. Then it's talking about your old refrigerator, which is kind of the energy hog for the electricity that you use. You can get a newer refrigerator that's more efficient, meaning that it uses less energy to do the same amount of work. You always want to use less energy to make sure that you heat your home or use your car 50 miles. Or you use the word efficiency when you're talking about how efficient you are at getting your work done, right? You spend less time to complete it. You're more efficient. We're always talking about how we want to be more efficient in general. If you wish to conserve electrical energy and save money, should you replace your refrigerator? How can you compare the energy efficiency of your old refrigerator with that of newer efficient models? So your old refrigerator uses 500 watts when the motor is running. The motor runs for about 30 minutes per hour, or a total of 12 hours per day. How much energy in kilowatt hours will you save by using the best new refrigerator instead of your current one? And how long will it take you to recover the cost of the new appliance? So the first thing it tells you to do, you can follow these steps. You can skip this to the next part. You know that your fridge uses 500 watts, so make sure that you convert that to kilowatts. This is the kilowatt right here. And then you multiply it by the amount of hours that you use it per day. That's this first step. And you try to figure out how many kilowatt hours it runs for the whole year. So there's 365 days per year. And then it tells you the new model uses 400 kilowatts per year. So it already calculated that for you and just gave it to you. What's the difference? Well, it takes the difference between the two, and it says that the new refrigerator saves this amount, this 1790 kilowatts per year. Now it tells you that you pay 10 cents per kilowatt hour. The new refrigerator costs you $5.50, but you receive a rebate, so it's really $500. If you replace your refrigerator, how long will it be before your energy savings compensate you for the cost of the new appliance? So if you saved 1790 kilowatts per year, you want to find out how much money you saved. So you figure out, because you pay 10 cents per kilowatt hour, that's $179 a year. But your fridge costs you $500, so you have to figure out, you have to divide these two numbers so you can figure out about approximately how many years it takes you to recover the cost. Okay, so it looks a little more complicated than it really is. It's just take it a little step at a time. Make sure that you're canceling out your units until you figure out your answers. All right, so this goes to your turn. Environmental scientists must often convert units in order to compare various types of energy. For instance, you might want to compare the energy you save by purchasing the energy-efficient refrigerator with the energy you would save by driving a more fuel-efficient car. Assume that for the amount you would spend on the new refrigerator from the previous problem, $500, you can make repairs to your car engine that would save you 20 gallons, or 76 liters, it already gave you the conversion here, of gasoline per month. Note that 1 liter of gasoline contains the energy equivalent of about 10 kilowatt hours. Using this information and table 5.1, I'll go back to that one, convert the quantities of both gasoline and electricity into joules and compare the energy savings. Which decision would save you the most money? All right, let's start with, what do I want to start with? Let's write down that it tells me a liter of gasoline is about 10 kilowatt hours. And you can take this problem lots of different ways. But I'd like to write down all my units here. It says convert the quantities of gas, so this question, and electricity from the previous one into joules. Oh, I can do that. That one's even easier. So let's start with that. Let's say that I save, let's do the car first, C for car. I save 76 liters of gasoline per month. All right, so 76 liters per month. I'm gonna write that down. Month. Right? Let's just write mo. I want to figure out, because the previous question was per year, so I want to figure out how many liters I'm going to save per month. There's 12 months in a year, or I mean per year, so there's 12 months in a year. 1 year. And that should cancel out the months so that I know how many liters I use per year. All right, so you guys will have to do the multiplication yourself right here, months per liters per year. And you would have to do this by hand. Remember, you don't get a calculator in my class, but you can check your work afterwards with the calculator when you're doing your homework. And I'd already previously calculated this myself, so I'll give you ahead of time. 912 liters per year saved of gasoline, okay? So now it says convert that into joules. All right, I'm still on the car. 912 liters. And if you remember, you go back to, what was it? This part, no, not right here. It already gave it to me. Oh, here we go. I got an equivalent here, liters to kilowatt hours. So I want to make sure that I use this equality to correctly cancel out my units here. That's sort of how I think about it. You could just remember that 1 liter is 10 kilowatt hours. 1 liter, 10 kilowatt hours. So yeah, you just multiplied that by 10 to find out how many kilowatt hours you saved by updating your car. All right, so you could probably do that in your head already. That's 9120 kilowatt hours. And if you remember from the previous answer, the fridge already saved you less, didn't it? It saved you, what is the answer? 1790 kilowatt hours per year. So already know you're saving more energy with the car. But it still wants you to convert the electricity into joules. So what was that? 1790 kilowatts. So let's use a different color pen so I don't confuse you guys. So fridge, F for fridge. Same thing as this one. So save 17. Oh, no, I forgot to do something, huh? Of course. 1790 kilowatt hours. Fridge, it says convert both of these into joules. Again, you already know the answer that the car is going to save you more energy, but now it still wants you to convert them both to joules. And that one's easy because you can just use this guy right here. 1 kilowatt hour equals, I'm going to use 3.6 megajoules because that's going to be easier for me. Okay? So 1 kilowatt hour. Sorry about this slowness. 3.6 megajoules. Do my kilowatt hours cancel out? Kilowatt hours cancel out. The answer is in megajoules. Same thing's going to happen here. You're going to multiply it by 3.6 megajoules is 1 kilowatt hour. That's my kilowatt hour there. Cancel them out. Both answers are in megajoules. This is all just converting things. And this is Kia problems now. So let's do a little Kia problems. Let's use green for this one. Atomic number, uranium-235. You're going to see that one a whole lot too. Has a half-life of 704 million years. Radioactive decay of 1 kilogram releases 6.7 tons of 13 joules of energy. You have to store it in a safe container, bury it deep underground until it drops to a safe level, which is generally after 10 half-lives. Assume that a nuclear power plant can convert the energy from 235 uranium, that's how we tend to write it, it's actually, the 235 should be small, into electricity with an efficiency of 35%. Electrical transmission lines operate at 90%, and fluorescent lights operate at 22% efficiency. So these questions are always nice and easy, right? Efficiency questions. You want the higher the efficiency, the better it is at making sure you don't lose energy, and you can still actually use the energy to turn on those lights, to turn on your computer. Overall efficiency, these are the easiest of problems, where you just take all these different efficiencies and multiply them out to figure out the total efficiency of the entire system. So I'm going to say, where did it start right here? The actual decay from this pile of atoms has a 35% efficiency. So let's say the nuclear power, the power plant. Oh, by the way, always convert these percentages into decimals. 35% efficiency. If you want, you can draw, like a pile of atoms. Oh, that looks terrible. Oh, Jesus. Okay, maybe not. I'm not going to try to be too fancy. To the energy in your power plant, which we'll talk about a little bit more as you keep going. 35.35. Transmission lines, so now the lines to your home, oh gosh, this is terrible, are 90% efficient, which is good. That's good. You don't lose too much energy from those guys. A little bit, because you lose a little heat, little sound. If you stand underneath them, you can hear them. And then finally they get to your house and they turn on your fluorescent bulb. Uh-oh, how am I going to draw you? And that bulb is 22% efficient. So overall, starting from the very, very first decay of your atoms all the way to the energy that's used to actually light up your home, you have a total efficiency of, I won't even tell you guys the answer, but you guys would have to multiply this out long. I'll know I have to for the next one, right? So it's about 7%. So we'd say 0.07 something something, 7%. How much energy from 1 kilogram is converted into the fluorescent light? Okay, so, well, that's kind of easy because you just calculated the efficiency of going from the decay to the light. It's 0.07. And you know that you have 1 kilogram of this is going to be converted into fluorescent light. So let's convert the kilogram into energy first, which I think was somewhere up here. Let's see. It said a kilogram releases 6.7 times 10 to the 13. So let's do that. 1 kilogram of uranium, blah, 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 6.7 times 10 to the 13. Is that right? I'm going to go check in that just a second. All right, so if I only had my stack of uranium-235 atoms, they would release 6.7 times 10 to the 13 joules. So I know if that's what they originally could release, the total amount that they do release, and it's only about 7% efficient, that means that only 7% of the energy originally found from that stack of atoms is used to light my fluorescent bulb. So I just figure out how much that 7% of that amount of energy is. Easy enough, right? Okay, good. And then it says, how long would it take for the radiation from a sample of U-235 to reach a safe level? It mentioned something about it's considered safe after 10 half-lives, and it tells me that one half-life is 704 million years. And we'll talk about half-lives more too. So, all right, one half-life, I write when HL is equal to 704 million years. 704 million. You can write million if you want, million. I have to now because I'm kind of insane about units and I like to make sure I follow them. Okay, so one half-life is 704 million years. I need to get to 10 half-lives, so you already kind of probably know how this is going to work. I know one half-life is 704 million years. In order for it to be safe, it needs to be 10 half-lives. And since they're giving me the conversion, or they're making me start with 10 half-lives, basically they're saying 10 half-lives equals how many million years half-lives. Then I'm going to use this equality. Of course, I have to flip it so that half-lives is at the bottom. And 704 is at the top. 704 million years. So you already know what that is. I won't have to tell you the answer. Million years. Okay? So make sure you write the complete answer on your page, but always show your work, especially crossing out units is a big bonus in general. The answer will be in million years. Or you can write out, the entire big old bunch of zeros there, and it'll just be in years. But I will accept million years in this case.